Okay, welcome to screencast number 2 on parallel circuits and their nature and how to analyze them. Again, here's a circuit that we're looking at on the right. It is a parallel circuit. I can tell because there's more than one path between the point of high potential and the point of low potential. This red positive side over here and the blue negative side over here are your points of potential. The blue is the high potential. It's negative. It's where the electrons are going to come out fully charged. And then the red on the left hand side is your low potential. In fact, I would call it zero potential. It's at the point at which the electrons have used up all their energy and have no ability to do anything else. And they will always move from high to low. And because of the arrangement in parallel, what we essentially have here is this whole section, and therefore this side of these two electron resistors are attached to the low potential point, and then this side is attached to the high potential point. Anything between the red and the blue are going to get the same potential difference in this case as the battery. So they're going to get 6 volts. So if we start going through and answering the questions here, there's a voltage drop of 6 volts across each 2 ohm resistor. Uh, the battery will increase the potential of the electron by 6 volts, add energy, and then each resistor will take away 6 volts. And essentially, again, that's a measure of the joules per coulomb, so therefore the energy being changed. By Ohm's law, if we're looking for the current, I equals V divided by R, so we have 6 divided by 2, so that's going to be 3 amps through each one. So going from this direction, each one's going to get 3 amps. Now we could check that pretty quickly at the junction here in terms of how much goes in later on and compare that to how much goes out and see how it works. The current in the battery. So the going back again to that junction idea, 3 amps goes up here, 3 amps goes down here. Now that means that 6 amps have to come in, and therefore 6 amps is at the battery. And if we go back to Ohm's law at the battery, the total resistance of the circuit is going to be equal to the potential difference in the circuit divided by the current flowing in the circuit. We have 6 and we have 6. 6 divided by 6 is 1 ohm. So here we have two 2 ohm resistors, and when we put them in parallel, they end up being equal to 1 ohm. So the resistance got less. And that is exactly what happens in parallel circuits because we're providing more pathways for the electrons. Okay, now in our first case there, both resistors were the same value. They were both 2. Anytime you have resistors that are all the same value, you can just take their value and divide by the number that you have. In this case, it was 2. And you would get 1 ohm. Now, if they are of different amounts, then you'll have to resort to the sum of the reciprocals being equal to the reciprocal of the overall equivalent resistance. Now this is a tricky one, although it's really simple with a calculator that has an x to the minus 1 key or a 1 over x key. So as we go through some practice on those, I'll show you how that works with this one down below. But you have to resort to that if they're not the same. As long as they're all the same, you can take this shortcut because the math works out exactly the same. Okay, so here we have a parallel circuit again, and we're going to try to figure out the equivalent resistance of the whole thing. Now this time they are not equal, so I can't just take and divide by the number that I have. I need to actually use the mathematical relationship. So what I'm going to do is use this key right here, x to the minus 1. And essentially it's 5. It's 1 over 5, so 5x to the minus 1, plus 4. And it's 1 over 4, so it's x to the minus 1, plus 7, and that's x to the minus 1. That'll give me a number. Now it's going to be a decimal number every time. I'm not done yet because that's 1 over the equivalent resistance. So my last step is to say x to the minus 1 and get my final answer. So it's 1.6867. I'm going to round that off just to 1.7 for our purposes. Okay, so it'll be 1.7 ohms. Now, one of the checks you can do on that is it always has to be smaller than the smallest resistance. So it had to come out to be less than 4, and it did, so that's good. Looks like we're on the right ballpark. Okay, to determine the overall current in the circuit. Well, we have 30 volts of potential difference over here, and again, this is all between the positive side, and then the lower half is all between the negative side. So the voltage across each one is 30 volts. Okay, so we're just going to take Ohm's law. It says that the current flowing in total will be the potential difference from the battery, in this case, divided by the total resistance of 1.7 ohms. And the total potential difference is the 30 volts from the battery. And 30 divided by 1.7 gives us 17.6 amps. Okay, potential difference across the 5 ohm resistor. Again, that has to be from blue to red. That has to be exactly the same as the battery. I don't need to do anything else. It's on one loop with the battery. The voltage in is 30. The voltage out has to be 30. Current through there will be then I equals V divided by R. But this time I have to use the individual resistor of 5, but it's 30 divided by 5 is going to be 6 amps. Current through the 7 ohm resistor is just going to be I is equal to V divided by R. It's again 30 volts. Okay, because it's in parallel with the other, they have to have the same exact potential difference, but it's going to be divided by 7 ohms, and then it's 30 is 4.3 amps. Okay, now we could make a quick check here just to make sure everything's going okay. We know we're putting in from the battery 17.6 amps of current. And we know that we got 6 amps going this way and 4.3 amps going this way. Now, if all goes well, the difference should be going up this way. So let's check that one. That's 30 divided by 4, and that's 7.5. And if we add them all together, they should come up to be about 17.6. So 6 plus 7.5 plus 4.3 gets us 17.8. Okay, within 2/10, that's close enough. We're good to go. That works. Also notice that the smallest resistor gets the biggest amount of current. That's always going to be true. If you are trying to figure that out, a simple ratio would work, especially if the numbers were simpler, like one was 10 ohms and one was 20 ohms. The 20 ohm would get half as much current. The 10 ohm would get twice as much current because it's half the size in terms of its resistance. So those are ways to go around checking the parallel circuit. And all the current flowing through the circuit branches, these are the branches here, must be equal to the current coming into the branch, and that's true of the junction in the coming in, the junction going out. And then the resistors that are smaller must always get more of the current. Okay, so these are false, so let's take a look. If resistors are connected in parallel, then the electric potential will be greatest across the resistors. The current will be the least across the resistor with the greatest resistance is true, but not the voltage drop. Voltage drops delta V are equal all the way across. And then again, in parallel, it's not the current that's going to be the same, it's going to be the delta V, it's the potential difference that's the same. In series, it's the current that's all the same, and then the resistor with greater resistance will have the larger voltage drop. So these true statements would be true if we were talking about series, but they're exactly the opposite in parallel. Okay, so a 2 and a 4 are connected in a parallel circuit. The potential difference is 4 ohm resistor will be, and the potential difference across the 2 ohm resistor will be And this is another case of those, it doesn't matter what the size of the resistor is, it's the same. If you're talking about the potential difference, it's exactly the same. Now this time it's asking about the current. Now the current in the 4 ohm resistor will be 1/2 of the current, so 2 times less, through the 2 ohm resistor. The smaller resistor will always take more, and it will take more in the ratio of the resistances. So if the first resistance is twice as large, then the other resistor will get twice the amount of current. Okay, that's the basics of parallel circuits. We'll use that in series circuits to define all the ways to analyze a combination circuit next.